This is lesson 66, BHDL example 41, and in this example we'll use a single D flip-flop to produce a divide by 2 counter. Here's the symbol for a D flip-flop, just a square box with D coming in and clock coming in. This little triangle here indicates that it's an edge-triggered D flip-flop, means that on the rising edge of the clock, Q gets whatever D has. And we're going to take not Q0. This bubble indicates not, so here's the output Q0, and then not Q will give not Q0. So we're going to connect not Q0 to D, just like that. So the equation for D is D equals not Q0. Now, suppose that the clock is low to begin with. Suppose Q0 is low. We've cleared it. We'll actually make an asynchronous clear in here, which I don't show on this D flip-flop diagram. And D, which is just not Q0, will be high. Since Q0 is low, not Q0 will be high. So suppose it starts out that way. And now suppose we produce a clock pulse. Well, on the rising edge of this clock, what happens? Well, Q0 gets D. What's D? Well, D is 1. Therefore, Q0 goes to 1. And it will stay 1 until the next rising edge of the clock. But as soon as Q0 goes to 1, then not Q0 goes to 0. So now D is 0, Q0 is 1. So what's going to happen on the next rising edge of the clock? Well, Q0 is going to get whatever D is. But D is now 0, which means that Q0 is going to go to 0. Of course, as soon as Q0 goes to 0, D0 goes to 1, and will stay there until the next rising edge of the clock. On the next rising edge of the clock, Q0 gets D, which is now 1, and therefore Q0 goes back to 1. As soon as it goes to 1, D goes back to 0, because not Q0 goes to 0. And now, on the next rising edge of the clock, D0 is 0, so Q0 goes back to 0, and D goes back to 1. So this is what happens. So what do we have here? We had a clock coming in, and the output Q0 is also a square wave at half the frequency of the clock. So it toggles on every rising edge of the clock. So on the rising edge of the clock it goes high, stays high till the next rising edge, toggles to low, toggles to high. We call this a divide by 2 counter because it takes the frequency of the clock coming in and divides it by 2. Why a counter? Well, we can think of this as a 1-bit counter that just counts from 0 to 1. So it goes 0, 1, 0, 1, 0, 1. Not too interesting, but we did produce a clock at half the frequency of the clock. Let's see how we implement this in BHDL. The inputs will be clock, clear, the output Q0. We'll need a signal D and Q. Then D is just not Q. And then we'll just make a process for our D flip-flop like we had in the previous lessons. We'll say if clear equals 1, then Q gets 0. That's our asynchronous clear. Else, remember clock tick event and clock equals 1 means rising edge of the clock. Clock tick event and clock equals 1. We have an event on clock and it ends up at 1. That's a rising edge. So on the rising edge of the clock, Q gets D. And then we'll just set the output Q0 to Q, this signal Q. And we can check it by doing the simulation. Here's the input clock. We'll start out with clear as 1 for a little bit and then bring it to 0. When clear is 1, that's our asynchronous clear, so Q starts out at 0. D starts out at 1 since it's not Q. And then on every rising edge of the clock, Q toggles as expected, and we end up with a clock frequency out, which is half the frequency of the clock coming in. So in fact we have made a divide by 2 counter.